Hello, welcome to the review of Quiz 7. This is on confidence intervals. So, yada yada yada, there's a link to the Z table, which I have opened here. So I've got this ready and waiting for when I need it. And off we go. So, question 1. So we've got some vocabulary questions, right? So, error due to unrepeatable and unpredictable influences. Well, there are a lot of choices here. Unrepeatable and unpredictable, well, that means random, right? I guess it could be due to incompetence, but that's certainly not something we've discussed. That's definitely a red herring here. That's not a real answer. All right, error that obeys patterns and that may be predictable. Aha, that is systematic error. The expected value of error squared is the same as. Which of these could that be? It could be standard deviation, except error squared. No. That's variance. That is the variance. Measure of error magnitude that has the same units as the measurements. Okay, so hysteresis we haven't talked about, and that wouldn't be it anyway. Z is a dimensionless number, right? Yeah, Z is dimensionless. It doesn't have the same units. That's standard deviation. A dimensionless measure of error magnitude. Oh, yeah. That's the Z value. There we go. Okay, so those are our five questions there. Now, we get into the real calculation. So, a voltage signal tends to give noise with about... Now, if these numbers aren't the same as what you had, don't fret. These quizzes generate random numbers, right? So they're not necessarily going to be the same as what you had. The important thing is the procedure. So voltage tends to give noise with about certain standard deviation here. You take a single measurement that reads 1 volt exactly. Your reported measurement with a 97% confidence interval is, so you're always going to report your nominal measurement. This is what you think it is, right? It is 1 volt, plus or minus what, in order to achieve 97% confidence that it lies within that range. Okay, well, to do this, we need to know what Z value gives us 97%. Why? Well, let's look for a moment, right? So which Z value gives us 97% confidence? So when we report a measurement, remember it's going to be the nominal plus or minus the standard deviation times a Z value, right, to establish our confidence interval. We've got the standard deviation, we've got the nominal, all we need to do is figure out what Z corresponds to 97% confidence. Well, let's have a look at our Z tables. Click. So remember these Z tables just give you 1/2 of the confidence interval. They don't give you both sides. So we have to take our 97%, or 0.97, and divide it by 2 to figure out what we're looking for. What's that going to be? That's going to be, those of you who said 0.985, or excuse me, 485. Yeah, that's correct. We're looking for 0.485 as half of 97. Oh, here it is. Right here, 0.485. So the question is, what Z value gives us that 0.485? Well, it's going to be 2.17. 2.17. So, if I click back to my work, so we have a value for Z. So then X is going to be 1 volt plus or minus, oh, I've forgotten what in the world was my standard deviation. It was 0.0046 volts. Notice that that's where we pick up the units on this, so it's going to have the same units as X, times Z, which is 2.17. There we go. So notice that the window that you actually achieve here is substantially larger than one standard deviation. It's more than double, as a matter of fact. All right, so 0.046 times 2.17. I mean, basically plus or minus 1. So you got 10% uncertainty there. That's a lot. And that's all in volts. Okay, so the answer we were looking for this one is going to be, I would enter 0.0998, which is crazy precise. All right. Vibration causes error in the readings from a pressure gauge. The error appears random. Hint, hint, it's not systematic. With a standard deviation around 0.8, right? There's a clue in this language that I'm hoping you'll pick up on, is that it's rare that you ever really know what a standard deviation is. You approximate these things, right? They're useful values to help you understand amounts of randomness, but my language reflects that these are approximated. How confident are you that any one measurement is within 1 psi of the actual value? Well, for this we're going backwards, right? So I didn't give you a nominal. So this is quite interesting. This is backwards. So again, so we know we want to be within 1 psi of the actual value. So what it means is this needs to be plus or minus 1 psi. Okay, so sigma times z must equal 1 psi. Well, if we know that sigma is 0.8 psi, and notice that this is psi per psi, right? So both of these have units psi. So z is dimensionless. So now we can go to the z table and look up 1.25. And here's what we get. There. All right, so 1.25, or yeah, 1.25. 1.2 is here, and then I need to come over and find 5. It looks like it's here. Let me make sure I'm looking at the right column. Yep, I am. So 394. So that goes to a P of 0.3944. Right? Now, that's only for, again, that's only for 1/2 of the confidence interval. But if I want to know what's the probability that my answer is within 1 psi to either side, right? So I need to double that. So my actual probability is double that. So my probability is 2 times 0.3944, or let's see if I can get it in my head. So 0.7888. There we go. So about 78.9%. There we go. And you knew you needed to do that because I'm pretty specific here. All right, 78.9%. All right. Use a faulty set of calipers. Oh, tisk tisk. Shame on you. To measure a set of gauge blocks. The error appears to be random and is only within 8 mil of the actual value. 86% of the time. Approximate the standard deviation. So okay, so here what we have is we know probability is 86%. And we know that sigma times z is 8 mil, right? And the question then is, what is sigma? Okay, so we'll use the 86% to figure out what z is, and then we'll have it, right? So no problem. So we need to look up half of this, so we're looking for 0.43 is the value we're looking for. I click over to the z tables. All right, we want 0.43. All right, so somewhere between these two. It looks like, yeah, this one's closer. I could interpolate. I'm not going to bother. So 1.48. So z is approximately equal to 1.48. Yeah. So then sigma is equal to 8 mil. Oh, I'm not going to carry it any more than that. That's already an insane number of decimal places. There we go, 5.41 mil. So it's about 5 thousandths, right? About 5 thousandths of an inch is the standard deviation. A little higher than that, but that's about it. Okay, we're almost done. All right, a rangefinder measures distance with about 52 feet of standard deviation in the measurement. If you measure a number that's in the ballpark of half a mile there, 5,280 is a mile. So if you measure about a half a mile, how would you report a 90% confidence interval, right? So again, the nominal measurement is just represented precisely as it is. So we want to know, so P then is 90%. So we're looking for half that, which is 0.45, right? That's the number we're looking for in the z tables. Z equals doc. All right, we're looking for 0.45. Let's see what can be done in the world of, here we go, somewhere in here. So again, it's an even split. Each of these is equally close. So I'm just gonna be arbitrary and say 1.64. Let's say, how about there, 1.64. All right, click. So I've said z is equal to 1.64. And so now we need to construct the confidence interval. So sigma times z is, and I have forgotten what my standard deviation was, 52 feet. "52 feet sounds like a lot, but not when you're measuring a mile. 52 feet is about 1% error of a mile, right? In fact, that's where I got it from, it's 1% error. Okay, so yeah, your confidence interval needs to be plus or minus 85.3. So that's what we would enter here. So 85.3. Done. All right, well, thanks for watching. I hope that was helpful.